Okay? So small things with large charges create large lattice energies. And remember, lattice energy is that energy required to break everything apart. It's like one just giant Lego brick made out of 1,000 pieces. It's how much energy it would take to take each piece apart. All right? And if they're small in size and large in charge, that's how you'll know. We're going to quickly cover electronegativity and covalent bonding. And then we're going to do our main part of the day, which is Lewis structures. The rules for Lewis structures will be up here. I'm going to go over them faster over there, but if you need to refer to them or write them down, they'll be on that screen the whole time. You okay with that? Okay, so here we go. Covalent bonding. So in ionic bonds, we had a complete transfer of an electron from one side to the other because the nonmetal would take the electron from the metal, and life was dandy. But in a covalent bond, there are two nonmetal atoms that are hanging out together. If they're both nonmetals, then none of them can steal the other. So if you can't steal to get bigger, you have to share to get bigger. Okay? So, in these bonds, atoms share electrons. There are several electrostatic interactions in these bonds. There's an attraction between the electrons and the nuclei. There's repulsion between electrons, and there's repulsion between nuclei. I wouldn't stress much about all that fine detail, but just know they're going to share electrons in order to obtain an octet. You okay with that? All right, a couple of examples that are on here. You can see this is nitrogen. Nitrogen is diatomic. It's diatomic because when it's alone, it doesn't have a full octet. There's another nitrogen to hang out with to complete the octet. The nitrogen will share 3 pairs of electrons or form a triple bond with another nitrogen. All right? Oxygen is also diatomic. Okay? And since one can't steal from the other, they have to share. Oxygen will share 2 pairs of electrons or form a double bond. Okay? They're not super complicated, but we share electrons in a covalent bond. All right? Now, there are 2 types of covalent bonds, polar and nonpolar. Polar means it does not share equally, or it shares unequally, and nonpolar shares completely equally. And what are we sharing, losing, or gaining? Electrons, okay? And whether something shares or steals or loses has to do with its electronegativity. Okay. Now, an example of sharing but not equally is when I was a sophomore, I would share a car with my sister who was a senior. What that officially meant, car 2, 180-day school year. That was not really an equal sharing, right? Yeah, it was. Are you going to have a little brother or sister next year? Okay. Would you? Yeah, that'll work. That's probably a good thing. Did you share a car with your brother last year? Was it equal? It's definitely not equal, right? The older person almost always gets the car unless they suck it, right? You bought it? Oh, you bought yourself a car. Getting the head cold, so I can hardly hear for some reason today. All right. So even though my mom said we shared the car, we didn't share it equally. It was only sharing according to my mother. All right. Now, Although atoms often form compounds by sharing electrons, the electrons are not always shared equally. So for instance, fluorine will pull harder on the electrons it shares with hydrogen than hydrogen does. Therefore, the fluorine end of the molecule has more electron density than the hydrogen end. All right? So you're more familiar with H and O because everyone knows water is polar. But it's the same idea. All right? What will happen is the one that is more electronegative pulls the electron to that side. Since the electrons reside here more than they do here, it leaves this side just pretty much the nucleus exposed, which is positively charged. And then over here you have excess electrons, which is negatively charged. All right? So that makes a polar substance. Just people are still writing this down, so just for your information, polar just means two-sided. All right, we have a north and a south pole on our planet, so we could say our planet is two-sided, the north and the south side. Magnets have a north and a south. All right, they are polar, and then this molecule is two-sided. It has a negative side and a positive side. Now, it's really important for you to know that the negative and positive I'm talking about here are not full negative and positive charges like we had in an ionic compound. In an ionic compound, we make an ion by moving an electron somewhere. All right? Here, we're going to call it a partial positive or a partial negative. Yes is a little bit positive and yes a little bit negative, but compared to ionic charges, it's not quite the same. Are you okay with that? All right. So, here we have our polar substances. Question? Yeah, it's constantly spinning, and it's moving everywhere. But most of the time, it will be around the nucleus of the F, more than it would the H. So this certainly will flip which side is which, but it's like 90% this is the negative side, and 10% that's the negative side. So it's definitely not equal. Go ahead. All right, fluorine is pulling harder because it has a greater effective nuclear charge. An effective nuclear charge leads to really what the word we'll use more often is it has a higher electronegativity. I think that's the next slide. So we'll talk to that right now. Electronegativity will determine how well they share or if they share at all. Electronegativity is the ability of an atom in a molecule to attract electrons to itself. On the periodic chart, electronegativity increases as you go from left to right and from bottom to top. So that is the same we had for decreasing size. Small atoms will be extremely electronegative. Large ones are not. Go ahead. Right. It doesn't really want to share with anything. So it'll do its best job to steal. Right? You can't see it on this slide very well, but fluorine's electronegativity is 4.0. Now, what is that? It's 4.0 dBites, which is whatever. It just means it's big. Hydrogen, I don't know if you can see it. It's right here. It's 2.1. Hold on. It's got a pen over here. Are you going back to Roy? All right. Good luck down there. Say hi to your little brother for me. He won't remember me, but I'll never forget him. All right. Take care, friend. All right. So if this is a 4 and this is a 2.1. It's sort of like their mass in a tug of war. Well, if you have a 40-pound thing pulling on a 2.1 thing, the 40 is going to win every time, right? Unless they're wearing cowboy boots, like Gold was in that assembly, and the teachers lost the tug of war because he fell over. But moving on, I'm not bitter. All right. When we talk about electronegativity, we talk about the difference between these two values. This difference is 1.9. That's a very large difference, all right, especially for something that is polar covalent. So what that means is F is pulling with pretty much 1.9 times the force than H. So the electron, if it's just sitting here, and you have F and you have H, and one's pulling harder than the other, it's going to hang out by that more often. By moving that electron that way, if this is a molecule, we now have a side that's more negative and a side that's left more positive. Good enough so far? Okay. You should know a little bit about electronegativity. Over here, they're really high. Over here, they're really low. Easy enough? You should know the three highest electronegative atoms are oxygen, fluorine, and chlorine. And I drew them in this weird shape for a reason, because that's where they are, right? So, the higher and righter you go, excluding family 8, all right? And if they were here, they do have some electronegativity, but they're small. All right, so fluorine the most, oxygen the second most, chlorine the third most. You need to know those three are super high, and then it decreases pretty much as you move away from them. As you move left, it decreases, and as you move down, it decreases. Go ahead. There's always weird stuff when we get to the transition metals, and that's because we now are dealing with the D block, and the rules are just slightly different. All right, so far okay? Okay, so whether something is ionic, polar, or nonpolar has everything to do with the difference in electronegativity of the atoms involved. All right, here's just a general saying here, or not saying, but generalization. So if you have two atoms and you find their differences and they're less than 0.6, the substance will be nonpolar. If you find two and their differences is between 0.6 and 1.7, usually they are polar. Now there's an exception to every single one of these, but this is generally true. And then typically, if you are greater than 1.7, it is ionic. Now, we just had one that was greater than 1.7, but it wasn't ionic, and that was HF, correct? The reason HF is not ionic is because it's not a metal and a non-metal. Okay. Now, if you don't have those memorized, if you are asked a question about that, it would give you that range. But just for your information. Now, does anyone remember what I said about non-polar? What's a non-polar bond? It shares equally. So if you look at this math, it kind of makes sense. If the difference between the two atoms is small, then they're going to have to share. That's like twins sharing a car. Right? There's not a whole lot of distinguishable difference. Okay? But then we get here, and now the difference is pretty big, but not huge. So now they have to share, but it's not equal. And then ionic, the difference is so loses and the non-metal takes. just a couple of things. In general, metal, non-metal is ionic. And then, this will help you a ton. The closer the non-metals are to each other on the periodic table, the more likely they are nonpolar covalent. So if you just have to guess, if they're really close to each other, they're probably nonpolar. Like literally location-wise, if they're close to each other, they're probably nonpolar. All right? But if they're a little bit far apart, they are probably polar. And then in red, if F, and I should put O for oxygen, if FCl or oxygen is in the substance, it is most likely a polar compound. Well, there's a ton of exceptions to those generalities. Like N2O, their oxygen is in it, but it's also right next to N. So then you're like, well, which one do I follow? And the difference there is 0.5, so it's nonpolar. So these are just super generalized statements. Exactly, you have to do the math every time, but get you 99% right. Okay, when two atoms share, we already settled it, share electrons unequally, a bond dipole. Dipole means two poles, and we don't say it's a dipolar, we just say it's polar, but it means two poles result, the positive half and the negative half. The dipole moment, which is mu, produced by two equal but opposite charges separated by a distance r, is calculated there. Measured in dBis. You don't have to know that equation at all. It's just the difference. Now, a lot of times this thing will be written as a little like arrow with a plus sign on the end. The arrow is showing you where the electron density is going. And we have this little part at the end to show that it leaves this side positive because it went towards this side. You'll see that commonly. Okay, the greater the difference in electronegativity, the more polar the bond. All right, so HF is definitely very polar. HI is not very polar. You don't have to know anything about this except for if the dipole moment is big, it's very polar, and if it's small, it's not. Like you don't have to calculate it or even know what it is. You just have to know how to compare them. Okay. Now, what we get to do is pretty, I don't know, I like it. I don't know how you guys will like it. Here we go. So what we're going to do is spend the rest of the hour on what we call Lewis structures. Lewis structures are really important. All right? First thing I'm going to have you do, though, I'm going to have you reading, and I hate reading, but I rocked it somehow. Yeah. All right. Lewis structures are representations of molecules showing all electrons bonding and non-bonding. These are important because you're going to have to draw them, and you're also going to have to do some math based on them. Now, the overall rules, like everything I say in the next 7 or 8 slides, is over there. So if I don't go slow enough for you to write down every word on the big screen, they're over there. All right, so what we do, this is pretty much that, just written out a lot prettier. So when we're asked to draw a Lewis structure, the first thing that we are going to do is find the sum of the valence electrons. Will you take 10 seconds and tell your partner how to know how many valence electrons an atom has. All right, that was good. I heard the word family like 25 times. That's good. So the number of valence electrons is simply equal to the family, correct? Are we okay with that? Do you want me to get up and get you a better picture of that? You're good? Okay. All right, so since phosphorus is in family 5, it has 5. I have no idea what this thing is, but whatever. It has 5. Chlorine has 7, correct? But you have to account for the subscript when we do this. So we have 5 plus 21. So phosphorus trichloride has 26 valence electrons. Are we okay with that? Couple of nuggets here. If the thing is an anion, so this one is not, but if it was, and it had like a -2 up here, if it's an anion, add 1 electron for each negative charge, so this one would be 2, right? If it was a cation, which this also definitely is not, but if it was, it had like a +2 charge up there, you would subtract 1 for each positive charge. Okay? So when you do this, the number one thing that kids forget, especially when they're brand new at it, is they forget to look at the charge and to adjust the electrons based on that. Okay, now this one, it doesn't have a charge. So that's our first step. Find the number of valence electrons. Oops, I forget I have to do it this way with the both chain. Next, you're going to put the least electronegative atom in the middle. The central atom is the least electronegative element that isn't hydrogen. Will you tell your lab partner right now why hydrogen can't ever be the central atom? I can't hear well, so I didn't hear the word I was looking for. The thing I was looking for is the number 1. Hydrogen can only form 1 total bond. So could it ever be in the middle of anything? No, because to be in the middle, it has to be at least 2. All right? So never put hydrogen in the middle, even if it is the most electronegative atom. All right, now, how would I know which one is the most electronegative? That's hard. All right, we don't have to do math. On the periodic table, these are the high ones, right? These are the low ones. So look, chlorine, there's also an easier way, by the way, it's coming up in a second. Chlorine is more electronegative than phosphorus because it's over here and over here on the periodic table compared to phosphorus, right? I guess it's no higher, but it's definitely to the right. Are we okay with that so far? Okay, here's another way to know phosphorus goes in the middle. How many phosphoruses are there in this substance? 1, and how many are there of the rest? 3. Almost always, and I can't even think of an exception, the thing you have less of goes in the middle. Okay? So, we first count up the total number of valence electrons. Then we put the central atom as the least electronegative of them. And then, this should be like a dash and down here. Connect the outer atoms to it by single bonds. Okay, that's what these dashes are. The dashes are representing pairs of electrons, which is a single bond. So I have 1, 2, 3, 4, 6. Okay, so far over here, we put the least one in the middle. Fill the octet of the outer atoms. Oops, it's right there. Sorry. That should be an enter too, I guess. Connect the outer atoms to it by single bonds. Single bonds means 2 electrons are being shared. Next, fill the octet of the outer atoms. So that will be probably coming up here. So we put 8 valence electrons on each of the outer atoms. How come the outer atoms get the electrons first? because they're greater in electronegativity. Remember, electronegativity is the ability of an atom to attract electrons to it. If it has more ability to attract, it will get the electrons first. Okay? Now, this maybe was on the other slides and I didn't even look at it, but keep track of the electrons. So what that means is how many valence electrons did I have to start with? 26. That was only one answer, so I'm worried we've lost that already. Remember, this had 5, this had 7, this had 7, this had 7. We add those up, and we had 26, right? Okay. Now, count up how many we've used. It's fairly easy because there's 2 here, right? So there's 8 around all 3 of these, correct? What's 8 times 3? 24. So I've used up 24 electrons so far. I have 2 left over, which is nice. This one's very simple to do. All right? The final step then is to fill the octet of the central atom. Phosphorus is the central atom, so it had 2, 4, 6 valence electrons with it to start with once we put the things together. So it needs 2 more, correct? Keep track of the electrons. We have 26 valence electrons to deal out. We used 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. That was 24 plus 2 more. That's 26. So I do not have any electrons left. That's a super good sign. If I can get to 0 and every single thing has a full octet, then life has been fantastic. I'm done. Now, they don't always work out that way because that's too easy. Right? And that's just how it goes. We don't always have a perfect combination where everything gets an octet. In regular chemistry, we do, because we just want to keep things simple. But in AP, things get a little bit harder. Okay. Now, if you run out of electrons before the central atom has an octet, you have to form multiple bonds until it does. Okay? So the example up here is HCN. That one is cyanic acid, or an acid with cyanide in it. We put carbon here. We connected them with a line. 1, 2, 3, 4 dots were used. All right, let's check. How many valence electrons does hydrogen have? Tell your partner. 1. How many does carbon have? 4. How many does nitrogen have? 5. So add these up and you get what number? 10. Okay? So we followed the rules. We put carbon in the middle. We put H on the side, connected it, N on the side, and we connected it. And now we've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've used every available valence electron. And nitrogen's okay with this, because nitrogen has a full octet, right? Right here. But is carbon happy? No. So if we cannot octet the central atom, we must share pairs of electrons. So carbon and nitrogen will end up sharing 3 total pairs of electrons. And this would be your Lewis structure. You okay with that? Who's with me so far? Okay. Whoops. Keep doing that. Okay, so here are 2 practice ones. They're not too bad. But I'll pause the recording. I'll give you a couple minutes. You try and draw these 2 Lewis structures. Here, the CCl4, everyone had fine. Right? We'll walk through it fast. C has to be in the middle. Cl, 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 Cl. You connect all of them with a pair of electrons, which is typically written as a line. But for now, we'll just connect them all with a pair. Then to complete the octet of the outside atom, atoms. That's chlorine. All right. Now, chlorine, all four of them have a full octet. I had how many valence electrons to start, by the way? I had 32, correct? All right. So I come down here. I have 8, 16, 24, 32. That's a good sign. Does carbon have a full octet? Yes. So this one's easy, right? Okay. But SO3 gas is a little bit trickier. All right. Do you know why I put it as a gas? Why did I write that? Good question. It's because you're used to SO3 being something else. Remember what? Sulfite. Close. Sulfite. But this is not sulfite, but this will show you why sulfite is usually sulfite and not SO3 gas. So here we go. We have how many total valence electrons? You have 6 plus 3 times 6, correct? So how many is that? 24 valence electrons. And this is a good number. It's a multiple of 8. All right. So that should be good, but it's not going to. So here we go. We have sulfur in the middle. We're going to have oxygen, oxygen, and oxygen. And then connect each one with a pair. And then the next step says to complete the octet on the more electronegative or outside atoms. Okay, and that's where I would be. And the next step, now these are typically lines. If you drew a line, it's fine. I'm just showing the dots just to help us see. Okay, now the final step says to complete the octet on the central atom. But I'm out of valence electrons, right? I've already used all 24 of them. So I cannot complete this. Now I don't just move on and say it sucks to be sulfur. I have to fix that problem. So look at the screen, because I didn't explain this very well. All right. You need to erase one of the pairs of dots and share it with the central atom. Go ahead. Well, specifically, if it was sulfite, it'd be SO3, and you'd have a -2 up here. That's the main reason to know. Right. Okay, so now make sure, when I said the same mistake was repeated, a lot of you had not erased that pair. Now I'm going to draw this with how the lines look. It'd be S with 1 dash, and then 2 and 1, and O would be octetted everywhere else. Now, hold on. Okay, yeah. When I ask you to do a specific Lewis structure, do the dots. But if you're just doing it for the math we're eventually going to do, don't waste your time with the dots. Okay. Now, did anyone have this right? Raise your hands. A couple of you did. Okay, look at the screen for a second. It doesn't matter if you put the double bond there or the double bond there. But you can't put it in more than one place. Are you okay with that? Because then sulfur would have more than an octet. Okay, so who's with me so far? All right. We're going to learn about these because if the double bond's here, here, or there, it doesn't matter. We're going to learn that these are called resonance structures. And we may or may not get there in the next few slides.
So if it has to be like a triple bond, sulfur needed more. Would you have a double bond on other atoms instead of on the other oxygens instead of having a triple bond?
Okay, that's a super good question, and it actually leads to this next thing. He says, well, would I triple bond or just make another second double bond? Right? That's what you're saying?
Yeah.
Okay. I wanted to finish this. I forgot. That is the bottom part. that's on the right screen. It says if there is more than one acceptable Lewis structure, then assign formal charges. And we'll probably have to do those tomorrow. But then you chop the thing up and look at it, and the best Lewis structure is the one where it's negative on the most negative. So we will get there. All right, just getting rid of some of this real fast. This was our structure, right? And just to kind of make something sort of cool, this is SO3 gas, or sulfur trioxide. But all year we've had SO3 minus 2 as a polyatomic ion called sulfite. We were okay with that, right? Well, why do you think it usually is a minus 2 and not SO3 gas? Not ionic. All right. Because oxygen doesn't really want to have to share more than it has to. So if we can find 2 electrons that we would steal from a metal, well then life's dandy, and oxygen doesn't have to share a double bond anymore, and we can complete the octet on the sulfur atom, and life's way cooler. You okay with that? Oh, did I put him in the wrong spot? Okay, thank you. Does that make sense on why this is actually more common than SO3 gas? Yeah, this would be solid in it. By the way, if it's SO3 minus 2, it's hanging out with some SO3. It had to get those two from somewhere, like. Okay, but that'll explain why these polyatomic ions are the charges that they are. Okay, this one is the SO4 minus 2. Usually I have you work it through, but it's already drawn. All right, so the polyatomic ion, make sure you remember, if it's a negative, we add 2 things because we're talking about electrons. So we had 6, and then 4 times 6, and then the plus 2 came from here. You okay with that? And we end up with 32. This is the same thing with SO3 and sulfite. By adding the 2 extra electrons, we now can octet every single thing without having to have a double bond. Okay? And typically, if you write a Lewis structure for an ionic compound, it would only be for the polyatomic ion, because ionic compounds don't have Lewis structures. These are for covalent bonded substances. All right. So now, what we have here is what James was asking. And this is something we're going to have to get comfortable with. We won't be comfortable with it in 3 minutes, but we'll just talk. And you should definitely read this section. I'm going to put one ed puzzle about this. And I probably will. I'm not going to require them. But if you would like to practice, then definitely I would. All right. So if there's more than one Lewis structure that works. So this is carbon dioxide. Carbon dioxide could have 2 double bonds, or it could have a single and a triple on one side. Both of those structures actually work. And both of them do exist, by the way. But this one is the favored Lewis structure because of this idea called formal charge. So when we have to debate between 2, we do this process. For each atom, count the number of electrons in lone pairs and half the electron it shares with other atoms. So what we're saying here, it's this number right here. So we're going to take the valence electrons that oxygen has, which is 6. And then I'm going to count up how many it has with it. It has 2, 4, and then I take half of these 4. 1, 2, 3, 4, but this tells me to take half of it. So I have 6 valence electrons in oxygen, and here I have 6 that are assigned to it. Carbon is sharing all 8, so I take the 8 and divide it by 2, and that's where I got this 4. And then this half is the exact same as that half, so there's a 6. Now in this other model, let's see if I can move this X. In the other model, we do the same thing, and we end up with a structure that has a negative here on oxygen, and oxygen's okay with that. But this oxygen has a positive charge, and carbon cannot force oxygen to become positive. There's only one element in the planet that can make oxygen be positive. You know what it might be? Fluorine. All right, so this we would eliminate because it puts a positive charge on the more electronegative thing. Okay, I don't expect that to be with you. We'll start there again tomorrow.